Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics. This is the main paper 1 in the semester 1 of the BSc Electronic Sciences degree program. In this lecture, we are going to see the concepts related to the circuit implementation of Boolean expressions. Let us see the session outline for today's lecture. In this session, we are going to see the simplification of logical expressions and also the implementation of expressions into circuits. In the last lecture, we have come across lots of theorems and identities pertaining to Boolean expression. Even in one of the previous lectures, we have learnt about them. In the last lecture, we have recalled all the expressions, but we have not used that expressions very much for simplifying the Boolean algebraic expressions. What is the necessity for such a simplification to be done on the Boolean algebraic expressions? When we use these identities and also the theorems, namely De Morgan's theorems, we will be able to simplify a long Boolean algebraic expression, and when we reduce the lengthy expressions, the advantage we get is we will be able to use a very simple circuit. We will be able to get an understanding of how the simplifications are done and also followed by the circuit implementation by taking some example problems. But let us first learn how to simplify Boolean expressions, and together we will also learn how to implement the simplified expressions into circuits. So, let us continue and see how the simplification of Boolean expressions are done by taking up few simple expressions as examples. By manipulating a Boolean expression according to laws and theorems of Boolean algebra, a simple expression that will require few gates can be obtained. To see how Boolean algebra manipulation is used to simplify digital circuits, let us see this example, and this is given as the expression. Let us consider the expression y is equal to a bar plus b, and that is ANDed with a or b. Here the plus can be called as or, and within brackets when the expressions are written we call them as AND. Here there are three logical operations performed. We have already got an idea of what is a logical operation. The operations are like NOT, OR, AND, XOR, NAND, NOR, etc. All that we have learnt in some of the previous lectures. Now, we have got this expression for simplification. Here, this plus represents one OR operation between these two logical inputs, and here also one plus, there is one more OR operation, and these two OR operations are found to be ANDed. Here the bracket implies there is a AND operation performed here. So, it has two OR operations and one AND operation in the given expression. Let us see the circuit implementation of the given expression. For the given expression without any simplification, as such, when it is implemented into the circuit, how it will look like? Definitely we can make a guess here. There are two OR gates required because there are two OR operations, and also one AND gate is required. So, we have to use definitely 3 gates if we want to implement this expression into a circuit which could perform the logical operations on this expression. Let us see how it looks like. Look at this expression and followed by the implementation circuit. See, as I said, I have even not mentioned one NOT operation here. I thought the A bar could readily be given, but if we have the A and B inputs alone, then one more NOT operation is also to be performed. So, these are the two OR gates, and here one AND gate we have. Of course, to get this complement of A, we have to use one NOT gate also. So, typically speaking, there are 4 individual gates required, one NOT gate, 2 OR gates and one AND gate, totally 4. And when we look at the stepwise outputs, let us have the diagram once again. See, the input has A bar. So, here the input A is complemented using a NOT gate and we get this, and the B is directly given. So, A bar and B inputs are given to the OR gate here, we get a OR operated output. Same way A and B are directly given here for the second OR gate. So, it is operated by the OR gate here we get, and finally the AND gate combines them with the AND operation. So, it has 4 gates if we do not have a complement part as input directly. Now, by using the laws of Boolean algebra or the theorems, or even when we say the identities, list of identities we have already learnt. Using all that, if we are able to simplify the given equation or the logical expression, we will be definitely able to reduce the given expression. And what is the advantage? If we are able to reduce the expression by means of the operations, if we are able to reduce the logical operations involved in the expression, then we get an advantage of reducing the number of gates. So, let us see how the simplification on this logical expression is performed using the theorems, identities and the laws. Let us continue to take up the expression for further simplification. Now, using the distributive law twice, we can simplify the given expression in this manner. So, this is the expression we have seen in the previous slide. This is the typical expression we have taken up for our discussion, and by distributive law we can open the brackets here, the OR, the AND can be distributed across the variables. So, A bar B, BA and BB all separated by the OR operation we are getting. So, we are now very much equipped with the associative law, distributive law, the commutative law, all those laws. So, I am directly using the laws here by mentioning the name. I hope the concepts are clearer here because of the earlier learning of these laws. So, we are directly using the laws to simplify the expression. So, let us continue. And once we get this expanded expression, we can think about using some of the identities. What is A bar A? A bar A is 0. This is one of the identities which we have learnt in the previous lecture. And also BB is equal to B. So, this is one way of reducing the expression. We have removed this A bar A because it is 0. So, this simplified expression we have. This is the first stage using the identities. And after that we see B appearing in all the 3 terms here. So, take B common and we have this A bar plus A plus 1 as an expression appearing separately. So, B is ANDed with this expression that is given in bracket A bar plus A plus 1. Here the plus represents OR operation, that we have to keep in mind always. And one more time we can use the identity, whatever be the expression, odd with the term 1 will end up with 1 only. So, that identity is used here. So, it is A bar plus A plus 1. This expression given in bracket will have definitely a value 1. This is again by using the identity. So, we finally get the expression getting reduced to a single term B. Is there any operation involved in the final term that we have as B? Originally we had a very long term, lengthy term within 2 brackets, the 3 variables A bar, B, A, like that we had. And once the expression is reduced by way of using the laws, the identities and the De Morgan theorem that we have not used here. We will take up one more example, so that the De Morgan theorem could also be used for simplifying such lengthy expressions. So, here we are restricting ourselves with the distributive law and of course few Boolean identities. When we finally get the expression, we are very surprised because the final expression is a single term B. There is no logical expression involved in the final term at all. It is only B. Is there any operation required? Is there any gate required? No gate, no circuit is required. So, if we want to implement this expression into a circuit form, we need not require a gate at all. It is surprising really, right? Originally we had a feel of using 4 gates. But now after simplifying the same expression, we come to a conclusion that we do not require any gate at all, because the final term is just that the input is appearing in as the output B. So, the expression simplification plays a vital role in reducing tedious circuitries, in reducing the number of gates. We have taken, I think, a worst case here, because 4 gates finally are not required at all. No gate is required here at all to implement the given expression into a circuit. So, let us reaffirm the process that we have done. Since the output of the circuit is simply B, we do not need a logic circuit at all. It is enough we just connect the input B to the output for implementing the expression as a circuit. See, the expression finally ends up with the term B, not even a single logic gate is required. So, this is one example we have seen how to simplify the expression and implement it into a circuit. We actually do not require any circuit at all, because there was no gate involved in the final term. We will take up similar such expressions further and see how the simplification and implementations are performed. We will see that after a short break. Welcome back. We are learning about the simplification and implementation of logical expressions using the laws, identities, theorems into the electronic circuits using gates. We have taken up one example to understand how the simplification is important. Now we will take up one more example and see how the simplification and implementation are performed on Boolean logical expressions. Let us take up this example. Let's take another example. Construct a logic gate circuit using NAND gates only for this expression y is equal to a bar plus bc the whole bar. And in this expression, we have the complement inputs a, b, c the whole bar like that. So, the complemented inputs are required. That is one thing we understand from the expression. The second part is there is a condition given in the question itself. Construct a logic circuit using only NAND gates, or NAND gates only we have to use. When we try to implement the given expression using NAND gates as such, the implemented diagram is also shown in the slide, which is just implemented after having a look at the logical expression. Let us analyze it. There is a complement required, of course B, C with an AND complement. So, it is an AND output of B and C. So, when we have the typical A, B, C as inputs, uncomplemented inputs, the first duty is to get a complemented values or complemented input. So, for that here a bar alone is required. So, we are using one NAND gate as a NOT gate. The two inputs are tied up here. So, how to use NAND gate as different gates, that we have learnt in one of the previous lectures. The NAND gate is supposed to be the universal building block, because using NAND gates we can build all other gates. So, those concepts are used here. Now, let us see how that is done. So, this A bar is given and the B, C complemented, and so it is NAND output, B, C NAND output is obtained, and here itself B also could be complemented, C also could be complemented, and then kind of complex circuitry could be done. But when we have a look at this expression, we have a feel this is the complemented output of or NAND output of B, C. So, that is why we have used one single NAND gate, and these two are to be given to an OR gate, because here is the OR operation. But we are given one restriction here, we have to use only NAND gates. So, how do we design a AND gate using NAND gates? Again 3 NAND gates are required for it. So, we recall that from the concepts learned in earlier lectures. So, let us see this section which I am showing using by moving the mouse. This section is actually the OR gate using NAND gates. So, that is why we are using this section as an OR gate, and the final output is the ORed output of A bar and B, C the whole bar. So, when we count the number of gates, NAND gates used here, I think we are using 5 gates. When we do not simplify the given expression, directly try to implement the given expression into a circuit. Let us have a look at the diagram and count 1, 2, 3, 4 and 5. So, 5 NAND gates are required here to implement the given expression just into a circuit. Now, because we are able to simplify it further, first we have to check whether it is possible for us to simplify. We can give a try. Some of the cases the given expression could not be further simplified. In that case, we have to just implement the given expression into a circuit with the number of gates as suggested by the expression itself. But if possible, we will be able to simplify, we should be able to simplify. So, let us have a try at it. The further simplified implementation is also shown here. Now, this circuit is nothing but the previous circuit. It is just copy pasted here so that we could compare it with this second circuit that is depicted. When we just have a look at the second circuit, we are able to count only 3 gates, but still the output is the same. Y is equal to A bar plus BC the whole bar. What happened in the middle? See, we are making use of the De Moivre's theorem. Here A dot BC the whole bar, when we have it like that, by using the De Moivre's theorem, we will be able to break it into this two. So, in that case, here what is required for having this BC bar, we have 1, and here we have to give directly this A here. So, the final output is obtained in this manner. It is A and this BC is given, these two are given as input, and this NAND operation is performed on it. When we look at this expression, it is not similar to the given expression, but when we apply De Moivre's theorem on this with an AND considered at between A and BC, we will be able to split the expression in this manner. So, finally, we require only 3 NAND gates. So, 2 gates are minimized. We get an advantage of it. In the previous example, what we have selected, what we have done, all the gates are not required. Only the input is to be just given as output, that too only one input B. Whatever the values of A, whatever the value of B, doesn't matter, the output is always B. That is the conclusion we got from the earlier example. And in this example, what is the conclusion? By effectively using the theorem, I mentioned, no, we can use the De Moivre's theorem also for simplifying the logical expressions. So, by using the theorem, here we are able to minimize the number of gates by, we are able to reduce the number of gates by 2. Only 3 NAND gates are required. Here we have not written the expressions to simplify, just having a look at the expression, we are able to come to a conclusion 2 gates could be eliminated, only 3 are required. So, this gives another idea of reducing the given expression and finally implementing that into a logical circuit. Now, let us take one more such example and see how the simplifications are further performed. With the more analysis we do, the better understanding we will get. Here it is given as the simplification part alone. The circuit implementation is not given because that could be done at any point, but the simplification is highlighted here. Simplify the Boolean expression, the given expression, using the law, theorem and identity, whatever it is. So, here itself the solution is also done by, when we count the number of operations, as like the previous case, there are 2 OR gates and 1 AND gate, A and D AND gate. These 3 gates are required, that is the feel we have here. But by applying the distributive law, how do we simplify? See, first we open the bracket. So, it is AA, AC, BA and BC, all these are ORed as per the expression. Now, we know the identity AA is nothing but A, and further simplification is not possible here as far as this expression is concerned, the other 3 terms are concerned. So, what do? We take the A as common between these two, the A is found to be common. So, A is taken with among the 3, the A is common. So, we have taken A as the common term and the remaining terms in the bracket, they are 1 plus C plus B. And once we have a look at this 1 in the bracket, we very well know by using identity, the whole term will vanish and the value will be just 1. So, A and 1 ANDed with 1 is just A itself, because that is the identity. A will not alter the given input. So, finally, we get A plus BC as the output, and BC cannot be simplified further it remains as such, it is to be kept as such in the expression. BC could not be further simplified. Finally, let us count the number of gates required. It is one OR gate here and one AND gate here. Only 2 gates are required. So, we are able to reduce it by 1 gate. So, that is an advantage. When it comes to the circuit designing, we will be using the integrated circuits. I have already introduced how the gates are embedded in circuit in IC chips. The IC gates I have already mentioned, that the numbers and everything we have seen. The number of gates reduced will have an effect on the number of ICs reduced. If the number of ICs reduced, the power consumption is reduced in the circuit design. So, there are, as like a chain reaction, one after the other, there are advantages getting added up. Finally, we will be able to reduce the cost of implementing the given expression into circuitry. So, finally, we come to a conclusion that when logical expressions are given, we should try to simplify to the last stage, the simplest expression we have to bring, and then we have to implement into a circuit. Without reducing or without simplifying the expression, we should never implement that into a circuit. We should bring it to the simplest form as possible and then go for circuit design. Let us see, this is the conclusion given for the previous problem. The original expression requires 2 OR gates and 1 AND gate, and after simplification, we need 1 OR gate and 1 AND gate. And this is one interesting case. The outputs of 2 NOT gates are ORed as shown in the figure. What is this combination equivalent to? Here, rather than giving the expression and asking us to go for the simplification and implementation, here there is an implemented circuit itself, the reverse. This circuit is to be analyzed. We should try to reduce the circuit itself as possible. So, we have to write an expression for this given circuit and try to minimize the circuit. So, let us attempt this problem also. So, have a look at the diagram first. There are 2 inputs A and B. They are complemented using NOT gates. So, A bar, B bar, we have the output. What is this combination equivalent to? So, that is what is asked in this problem. So, when we have a look at this, when we try to approach this problem, from the logic circuit, it follows like this. Y is equal to, the output is equal to the input A bar plus B bar and the whole bar, it is OR gate, NOR gate. So, NOD, it is NOD. By applying De Morgan's theorem, we will be able to break it into simple terms and we get A dot B. It is just a AND operation. Only one gate is enough. The 3 gates are not required. Just one gate is enough to perform this operation. Like this, we can take up lots of cases and learn. There is no end for this training, but let us put an end to this with these 3 examples we have taken up for discussion. Actually, we have done 4 examples. Now, it is time for us to look at the summary of what we have learnt in this lecture. In this session, we have seen the simplification of logical expressions and the implementation of expression into circuits. Let us test our understanding by answering these questions. Simplify the following logic expression using laws and theorems of Boolean algebra. Of course, we can use the identities. I have just picked up 2 such expressions. Both are one and the same. The question is the same. Here it is given as the output y is equal to something. Here it is given as the logical expression. We should prove what is given on the left hand side is to be proved for the expression given on the right hand side. It is a simplified expression. You can try your hand in these 2 expressions to simplify them. So, it is time for us to wind up this session. See you in the next lecture with the concepts related to the simplification of given expressions, not by using the laws, theorems and identities, but by some higher techniques. So, thank you for